Introduction to Limits. You can follow along with this video with the handout called Introduction to Limits, either blank or filled in if you'd like to. Before I start the examples, I want to explain why we are talking about limits. Limits are the basic building blocks of calculus. They are the theoretical basis for calculus. And limits are also the most difficult part of calculus. In real life, limits were kind of intuitively understood and used for calculus computations for about 300 years before calculus was ever formally proved mathematically. Many mathematicians were very skeptical about calculus because it was very difficult to grasp why it worked, and you'll see a little bit of that as we talk about limits. But finally it was proved, and the proof is one of the most difficult proofs I've ever seen. Unfortunately, when we teach calculus, we start out talking about limits and that proof. And so calculus seems absolutely ridiculously hard when you first start it. But let me tell you, if you get past that theoretical basis, realize that's the hardest part of the course at the very beginning. And so don't give up and quit and think I can't do this and it's only going to get worse. It actually gets better after the beginning. So just a word of warning, when you go into a calculus class, that will probably happen. You'll hit that theory first and it's very difficult. So we're going to talk about a little bit of it in sort of a more intuitive way, hopefully help you through that transition next year. My first example is a football example. Let's say we have a football team that's 10 yards from scoring a goal. If the defense is charged with a penalty, the offense will gain at most 5 yards, which is half the distance to the goal line. If the team is now 5 yards from the goal line and the defense is charged with another penalty, the offense will again move half the distance to the goal line, or 2.5 yards. And so forth. If the defense continues to be penalized, the distance the offensive team from the goal forms the sequence: 10 yards, 5 yards, 2.5 yards, 1.25 yards, 0.625 yards, etc. What would happen if the defense were charged with an infinite number of penalties? Could you ever score a touchdown? Okay. Well, your first answer probably is no, because you just keep going halfway to the goal, halfway to the goal, halfway to the goal, and you never get there. If I were to draw a little graph of this situation, this could be the number of penalties on the x-axis, and this could be the distance from the goal on the y-axis. And before we had any penalties at all, so at 0 penalties, we started at 10 yards. And then with 1 penalty, we went to 5 yards. And then with 2 penalties, we went to 2.5 yards. And with 3 penalties, we went to 1.25 yards, and so forth. And each time we're cutting that distance in half. And you're going to get something that goes down gradually and gets closer and closer to the x-axis, which you would recognize as an asymptote. So we would say as the number of penalties goes to infinity, we would say that the distance to the goal goes to 0. But the question is, can it ever equal 0? And the answer to that is yes. If you have an infinite number of penalties, it will equal 0 according to mathematical theory. Now that's kind of weird, so I just want you to think about that. So we write it this way: that we say the limit as penalties go to infinity of the distance is equal to 0. So that's how we write it mathematically. Okay, second example now is the infinite sum example. And this is something that hopefully you have seen before, but I'm going to just talk about it again. Let's say we add up a series of fractions: 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1 over 32, and so forth. You'll notice that these are getting half as big each time. So we're multiplying each time by 1/2 to get to the next one. And you should recognize that as a geometric sequence. This is a geometric sequence, or a geometric series we call when we add them together. And let's just use this square here as an example of what this sequence represents. So let's say that each of these numbers represents a fraction of this square. So we're going to start out, we have half of the square. And if we want to say how much of the area of this square is covered, then I can color in, I'm going to color in and say that so far we have half of the square covered. Okay. Then if we add the next one, we have 1/4 of the square covered. So now we have another 1/4. So now we have 3/4 of the square covered. And if we add 1/8 to this, and we color in another section, oops, that wasn't what I meant to do. We'll try that again. So 1/8. I'm having a little trouble with my cursor, so hopefully it will not give me fits. Now we have a total of 7/8 covered. So if you remember our language from sequences and series, the first sum is 1/2. The second sum is 1/2 plus 1/4, which is 3/4. The third sum is 1/2 plus 1/4 plus 1/8, which is 7/8. The fourth sum, then we're going to add plus 1/16 to that. And so we end up with 15/16. Because 7/8 is 14/16, we add another 16th and we get 15/16. As a matter of fact, if you notice the sequence, we have 1/2, 3/4, 7/8, 15/16. The next one is going to be 31/32, and we add the 1/32 to it. So we can add this, we can add another one, we can keep doing this. And notice what happens as we add 1/32, 1/64, 1/128, and this would be 1/256. If we keep adding all of these little sections, and we keep adding half as much any time, we keep filling in this corner. And if we kept doing this over and over, eventually we are going to get closer and closer to filling in the whole square. And you'll see that S sub n is getting closer and closer to 1. Now the question is, does it ever equal 1? Once again, the answer is yes, if the number of terms in the sequence goes to infinity. If it's an infinite number of terms, it equals 1. If we cut it off any less than an infinite number of terms, then it's only close to 1. But if it's an infinite number of terms, it equals 1. This is the weird thing about limits. This is the weird thing about calculus. And once again, you don't know how this relates to calculus yet, but this does relate to calculus. Let's recall that we had something about limits back when we did an infinite geometric sequence. First of all, there were certain sequences that converged that we could find that limit for, that sum. There were other sequences that diverged. For example, if I had the geometric sequence 2 plus 4 plus 8 plus 16 plus 32, that's just going to get infinitely big as I add more terms. But if the terms are getting increasingly smaller, then when I add them, I'm adding numbers and numbers that are getting closer to 0. Eventually, the sum doesn't increase any. And so the rule here is that here we have an r that's equal to 1/2. If the absolute value of r is less than 1, we say that the series converges to a sum. And that is actually a type of limit. And I might have even used this limit notation. The limit as n goes to infinity of s sub n is equal to the first term, a sub 1, over 1 minus r. Hopefully that looks familiar. And a sub 1 is 1/2. R is 1/2. So we say 1/2 over 1/2, which is 1. So we say the sum is 1 as we add an infinite number of terms. So we've done this, even though it sounds kind of weird that it equals 1, it equals 1. Now this last example is, to me, the most convincing that something that's going to infinity actually ends up equaling something. We have the repeating decimal, 0.99999, and it can be written as 0.9 plus 0.09 plus 0.009 plus 0.0009, etc. And you can see that we have here a geometric sequence. Our first term is 0.9, so a sub 1 is 0.9, and r is equal to 0.1. And we could use the sum of an infinite sequence like we just did. We can say the limit as n goes to infinity of a sub 1 over 1 minus r is the limit I didn't write that correctly. The limit as n goes to infinity of s sub n is a sub 1, which is 0.9, over 1 minus r, which is 1 minus 0.1. And that's 0.9 divided by 0.9, which is 1. So we're saying 0.9 repeating actually equals 1. So let's look at another way of looking at this. What if we said let x equal 0.999 repeating? Then 10x would equal 9.999 repeating. And if we subtracted x from that, that would be the same as subtracting 0.999. So if I subtract x equals 0.9999 repeating from both sides of the equation, on the left-hand side of the equation I get 9x. On the right-hand side of the equation, all the 0.9 repeating part subtracts out, I just get 9. So once again I get that x equals 1. One more proof that 0.9 repeating actually equals 1 is found by looking at our calculator. And I want to look at a particular, I went through and I did 1 divided by 9, which is 0.1 repeating, 2 divided by 9, which is 0.2 repeating, 3 divided by 9, 0.3 repeating, etc. And ended up with, now notice they round. When you get 5, 5, 5, it rounds. But that's still 0.5 repeating, 0.6 repeating, 0.7 repeating. So 8 over 9 is 0.8 repeating. So 9 over 9 should be 0.9 repeating. But 9 over 9 is 1. So it equals 0.9 repeating, and it equals 1. Interesting. Okay. So we have shown in several different ways that 0.999 repeating is actually equal to 1. Now these examples are why limits are so confusing, because in our mind we want to say, well, it's almost 1 but not quite. But we're saying if you take something to infinity, it actually equals something. Okay, that's the end of part 1. We'll do some more examples on part 2.